Welcome to dialogue about Western boundary boundary current systems. My name is Yasumasa Miyazawa, a researcher of Japan Agency Marine and Science Earth and Technologies, JAMSTEC. I have studied Kuroshio dynamics using data assimilative ocean general circulation models. In this talk, I summarize model-related Glocial research and discuss its possible connections with sustainable observing systems. Presentation contents are shown here. First, I briefly mention the Glocial dynamics based on both observation and modeling. Then I will show the operational modeling status for understanding the Glocial dynamics and discuss possible implications related with model and observational studies. Using the modeling methods, the dynamics of the Glocial has been investigated mainly from two views: forced and internal mechanisms. First of all, the Glocial is a part of subtropical gyre in the North Pacific Ocean, driven by the large-scale wind forcing. On the other hand, a combined analysis of both the in-situ and remote sensing data have elucidated those nonlinear interactions between the Glocial and mesoscale eddies affect the dynamical state of the Glocial system. The high-resolution OGCMs have definitely contributed to connecting the two views of the Glocial dynamics, internal and forced mechanisms. The volume transport of the Glocial is roughly determined by the Rossby wave dynamics forced by the large-scale wind, and the periodic occurrence of the Glocial large meander is a very unique aspect of the Glocial among the western boundary currents, as mentioned by the observation part of this discussion. A series of intensive OGCM studies, mainly conducted by the modelers of the JMA, Meteorological Research Institute, demonstrated that the general tendency in the occurrence of the Glocial large meander could be represented by the processes triggered by the wind forcing, large-scale wind forcing. The mesoscale eddies generated by the wind forcing are considered as the main player of the internal dynamics related to the occurrence of the Glocial large meander. Multi-decadal simulations of the eddy resolving OGCM with 10 km of the resolution is an effective tool for detailed investigation of the Glocial dynamics. And some researchers of JMA propose reliable Glocial large meander mechanisms driven by the large-scale wind forcings. Also, new development of ensemble simulation techniques is necessary for carefully diagnosing both the forced and internally driven phenomena in the Glocial system. There are still remaining open questions of the Glocial dynamics. The first is the links to climate, also frequently mentioned by the observation part of these discussions. And also offshore, nearshore interaction is still unclear. That includes Glocial intrusions to the coastal areas and possible coastal barriers against the Glocial intrusions. And the Glocial is considered as a nutrient stream. This kind of nutrient stream Glocial dynamics are still unclear, and also its implication to the marine carbon behavior is still unclear. And global warming effects on the Glocial system should be investigated in more detail. We need further efforts for development, new modeling, and observation methods for resolving such unclear scientific issues. To intensively examine roles of the mesoscale eddies in the Kuroshio dynamics, ocean data assimilation systems based on OGCMs have been developed so far past over 20 years. Operational ocean data assimilation system could be utilized for investigating the effects of the initial conditions representing the eddy distributions on the resulting evolution of the model dynamics. For example, a data assimilation system has demonstrated the direct trigger of the Kuroshio large meander in 2005 was warm eddy propagation from the East China Sea. At the present time, Japan Meteorological Agency, JMA, National Fishery Research Agency, FRA, and JAMSTEC are conducting the operational ocean data assimilation and the prediction of the Kuroshio path variations in near real-time basis. The predictability limit of the Kuroshio path variation is considered as approximately 1 month. The operational data assimilation systems assimilate the satellite altimetry data, satellite SST data, and in-situ temperature and salinity profile data using 3D bar and or 4D bar methods. The satellite altimeter data are most important for determining locations and magnitude of the Kuroshio path and surrounding eddies by providing the information on the main thermocline structures. The satellite SST data complementarily supplies the information on the surface layer related with the mixed layer variations. The in-situ temperature and salinity data are used for validation of the data assimilation system by checking the products without assimilating them. But the additional assimilation of the in-situ data provides us with the information about the limitation of the model and remote sensing data. And the tidal gauge data, and this mentioned by the observational part of the discussion, is mainly used for validation of the model behaviors like this. The additional assimilation of the product of the data assimilation system are now used for various kinds of the marine research and utilized for practical uses of the search and rescue, shipping, fishery, and marine engineering activities. The horizontal and temporal resolution of the OGCMs built in the operational systems have become improved step by step since the launch of the systems in the beginning of 2000. The present systems provide the information of the oceanic condition with 2 or 3 kilometer grid and hourly resolutions. The targets have gradually expanded from large-scale mesoscale to submesoscale, and the tidal currents have been explicitly represented by the OGCMs in addition to the geostrophic currents. An important unresolved problem is the dynamics of the Kuroshio intrusion into the coastal regions. We require a higher horizontal resolution of both of the model and observing systems for elucidating this unclear issues. We are planning development of a 200-meter grid OGCMs covering the whole of the Japan coastal ocean. The inside of each 200-meter grid, surf zone dynamics, not geostrophic mechanism, might be more dominant, and it is out of scope from the present research interest. But we can downscale to at least 200-meter grid for still representing the geostrophic phenomena related to the Kuroshio dynamics. The limitation of the model schemes includes mainly representation of the air-sea interactions. The momentum transfer from the atmosphere to ocean are simply represented by the bulk formula. The several studies indicate significant dependence of the Kuroshio simulation on the representation of the air-sea fluxes. A long-term simulation of OGCM demonstrates that the simulated mesoscale eddy activities and those relevant Kuroshio path variations changes significantly with or without difference between wind and ocean current velocities. And not only the ocean currents, but also the wind wave conditions at the sea surface also affect the momentum exchange at sea surface. The recent advance of such atmosphere, wave, ocean current interaction studies should be carefully introduced into the numerical schemes, I think. And also, the freshwater exchange at the sea surface also involves problematic issues. An OGCM simulation driven by the evaporation and precipitation data alone results in serious errors. The usual simulation still requires the flux correction with relaxation to the salinity climatology based on the field observations. The information of evaporation and precipitation provided from the atmospheric reanalysis data frequently used for deriving the OGCM still involves some non-negligible errors. The all results mentioned here imply that proper implementation of coupling atmosphere, wave, ocean, land without any kind of flux correction would be interesting future development for more reliable operational ocean modeling. In addition to the unmanned in-situ measurements mainly conducted by the Algo float, in Japan, local fishery agencies are conducting intensive measurements of the nearshore regions at least once a month. And also this is mentioned in the observational part of this discussion. This activity well covers boundary current regions and plays a unique role in Japanese oceanography, complementing the float observations in the offshore regions. It is worth noting these data are regularly reported to the WMO, the Global Telecommunication System, GTS, and forecast centers are providing the forecast information with assimilation of their data to the local fishery agencies. The observational system experiment demonstrate inclusion of the temperature and salinity measurements confined around local bay complementarily works for evaluation of the coastal current, which is never represented by the assimilation of the offshore remote sensing data product alone. The coverage and frequency of the satellite SST has been enhanced by utilization of the geostationary satellite SST data. The composite of high-frequency geostationary satellite Himalaya SST snapshots effectively reduces invisible areas caused by the cloud contamination due to the cloud covers, as compared to the traditional infrared sensors. Recently, a very active group of marine animal telemetry research in Japan is working for a possible transmission of their biologging data to global telecommunication systems. The measurement by sea turtles have a potential to enhance observations in strong ocean current and in bad weather conditions, for example, bomb cyclones. The new observation technology is developed to reduce missing coverage of the traditional observation instruments. One missing area in the Kuroshio region is the nearshore regions. Higher resolution remote sensing technology, including wide swath altimeter and advanced infrared imaging, will enhance such aspect of observation requirements. The higher resolution ocean modeling requires more dense observation with high frequency sampling in the nearshore areas. Now, some of Japanese oceanographer groups, including JAMSTEC, are constructing feedback systems connecting the model and observation toward enhancing the observation measurement sampling in the coastal areas. The oceanographer groups provide the fishery and shipping people with their forecast product, and the users provide their own observation data to the oceanographer groups. The forecast center provides a forecast product with improved skills by the assimilation of the user's data to the users. The improved skills of the forecast product strongly motivate the user to enhance their observation activities. Such feedback mechanism is helpful to sustain and enhance the observation system and the coastal areas. To more effectively manage the feedback system, we are developing the targeted adapting observation technologies based on ensemble model sensitivity theories. They eventually applied to the feedback system improvement. In the end, I emphasize that we need not only enhancing the observation system, but also improving the data assimilation systems. Sensitivity to assimilation of the observation data could involve significant system dependence. The comparison of sensitivity to the in-situ temperature observation data between the 3D bar and 4D bar schemes demonstrates more effective utilization of the remote sensing data using the 4D bar system as compared by using the 3D bar system. The close collaboration and intensive discussion among observation and model communities are needed for optimal design of the observing system targeting the Kuroshio system. The summary is here. That's all. Thank you very much. I really looking forward to meet to all of you on July 6th meeting. Let's discuss all detail of the Kuroshio system. Thank you very much.